Welcome to my channel. In this video, we will discuss the energy band diagrams in semiconductors. Before we really go into semiconductors, let us try to understand what is an isolated atom. This is an isolated atom. This is the nucleus, and these are the number of electrons and which will be revolving in the orbits. So this is the outermost electron. Now each these individual electrons will have different energies and they are discrete energy levels. So n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. This is according to Bohr's atomic theory. So all these individual energies of the electrons will depend on in which orbit they are revolving. So energy here will be different, energy here will be different for the electron. Now if we consider a solid, usually isolated atom does not exist. So solids are aggregate of atoms which have atoms coming closer together, and there will be, therefore these individual orbitals will overlap. There will be interactions, the electron interactions. Now these interactions can be between any two electrons or between the two nucleus, which will be very weak, so we will ignore, and it can be between one electron and nucleus or between this electron and this nucleus. So it can be between two electrons of the two atoms, or it can be between electron and nucleus, or nucleus and electron of the two different atoms, or between nucleus and nucleus. So usually these two electron orbitals will overlap, and because of the overlapping there will be a this difference will become very negligible like this, and it almost becomes a continuous energy variation, a continuous energy variation. Therefore the electron orbitals will overlap and it forms like a band, energy band. So that is what is an energy band. Now let us try to understand what are the conduction band and valence band, and in metals before we go. So if an energy band is filled with, if this is an energy band, if it is filled with valence electrons, this is called a valence band, and any band above this is called a conduction band. Usually valence band will be filled with valence electrons and conduction band will be empty, where it can allow the electrons from the valence band to reach the conduction band. So this is valence band and we will denote it as VB, and conduction band we will denote it as CB. What does that mean? Valence band will have all possible energies which are possessed by the valence electrons. So possible range of energies possessed by the valence electrons, and here it is above the valence band. Range of possible energies possessed by free electrons. Here any electron which is reaching the conduction band will be free, which is responsible for conduction. So these are the conduction band and valence band. Now let us see in the classification of materials in the last video which I discussed. Let us go in a little more in depth. Now metals, or you can say conductors. Now here there are two possibilities that you can have. Either you can have, this is a valence band and this is conduction band. Here this is valence band and this is conduction band. Now because of the overlapping of the individual electron orbitals, so you can see that these two are overlapping and there is no gap. So Eg is 0. The gap between conduction band and valence band is 0. Now the another case here is there could be a partially filled valence band. So here it is valence band and it is not completely filled, so it is partially filled. So from these filled valence band energy levels, the electrons can go like this to the above, where you have partially filled means another few electron energy levels where they can go. And then partially empty conduction band. So electrons can move within the valence band, or electrons can move from valence band to conduction band. Because of the overlap, they can freely move here in this case. So this is about metals or conductors. Then in semiconductors, as I have already discussed, there will be a moderate gap. Moderate gap, what is the range? This gap is in the range of less than 3 electron volts. Now this is valence band and this is conduction band. Now for germanium and silicon, which are examples that we have discussed, the values of the energy gap are 0.7 electron volts or 1.1 electron volts. So what does that mean? If the electrons, which are filled valence electrons in the valence band, if they have enough energy to be able to jump across, then they can reach the conduction band. Then available for conduction. So they will have the moderate conductivity or resistivity. Now in insulators, you have a wide gap. So the gap is greater than 3 electron volts, and therefore there are no free electrons. The electrons cannot jump across this gap because this is a large gap. So they will not be able to move from the valence band to the conduction band. Therefore there are no free electrons in the conduction band, and therefore there is poor conductivity in insulators. So in semiconductors, coming to semiconductors, what will happen when these, I mentioned here, these electrons can reach the conduction band. So when these electrons, so these are electrons, so let us say these 3 jump to the conduction band. So the electrons from here reached the conduction band here. Therefore they left a vacant space like this. So because they are empty, these can go and occupy this. So these are empty conduction band energy levels. So these electrons will go here and leave vacant sites, and that I call it as holes. So in a semiconductor, conduction is due to both electrons as well as holes in the valence band, free electrons in the conduction band, which jump from the valence band to the conduction band. So that's how the conduction takes place, and unlike in metals where the electrons are the only charge carriers for conduction, in semiconductors for conduction both electrons as well as holes are responsible for conduction. Now let us consider the case of silicon or germanium crystal containing N atoms. So let us see the comparison, how it goes with all these different parameters. Now silicon and germanium are most widely used semiconductors, therefore I am taking these two and discussing. Atomic number 14 for silicon and germanium 32. Now configuration, electronic configuration, when you write, you will have this. So 1s2 2s2 2p6 3s2 3p2, 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p2. Then in each orbital you have 2 electrons, 8 electrons each shell, and then the outermost 4 electrons. So 2, 8, 18, 4 here in germanium. Now you can see that outermost orbit is what? The third one. So n is equal to 3, and here in this case fourth one, n is equal to 4. But in each case the valence electrons are how many? 4. How many 2? 2 of S and 2 of P. So in the third state for silicon, here you will have 2 of S and 2 of P in the fourth state. So the state is different, though the valence electrons are the same in both the cases, the outermost orbit is different. This is far from nucleus, that is fourth state, and this is third state. Then if you consider the number of outer electrons in a crystal as a whole, this is for an atom. So in a crystal as a whole, how many you will have? How many number of atoms you have? N. Therefore, how many number of electrons in a crystal? 4n. Here also 4n. Then what are the maximum possible number of electrons? So maximum possible number of electrons in the outermost orbit, 2s and 6p, because you will have, if you look at the configuration, S you will have 1, 2, P you will have 3, 1, 2, 3, 4, 5, 6. So 6. So available are 6, but how many we have? Only 2. Only 2 we have. Similarly here, available are 6 in P, but you have only 2. So put together you have 8 outermost possible number of electrons that can occupy, but you have only 6 energy levels and 2 energy levels in the S. So maximum possible. So these are the possible. Now how many number of available energy states? Therefore 8n. Here also 8n. So these 8n available energy states, 8n available energy states in semiconductors, see, generally they can form a single band, all 8n, or they can split into 2 parts, and in semiconductors they split into 2 parts and 2 4n states which are separated by an energy gap at absolute 0. Absolute 0 means T is equal to 0 Kelvin. Now let us see that structure. So these are the filled valence band energy levels, 4n states. These are the empty conduction band energy levels, 4n states. That means the available 8n energy states are split into 2 4n states. 4n states here and 4n states here. So filled valence band 4n and the gap between them. Now what is EC and EV? EC is the lowest empty conduction band energy level. EV is the highest filled valence band energy level, and the separation between these two bands, that means it is between these two, the lowest conduction band energy level and highest valence band energy level, and these two difference is what we call it as energy gap or band gap, and this is also known as forbidden energy band. That means here you will not have any electrons available for conduction. And only when energy is supplied, electrons from the valence band, if enough energy is supplied, can reach the conduction band, and you will be able to have some electrons available for conduction in the conduction band. In my next video, I will talk about the structure of silicon and germanium and how they make significant contribution as semiconductors, and then I will discuss different types of semiconductors. Until then, keep watching, keep learning. Thank you.